So as we are discussing that stresses are of order 2 tensor, right? And there is separate mathematics available for tensors, and separate calculus, separate algebra is there for tensor. Their understanding makes the understanding of continuum mechanics much easier. By which I mean the notations comes down, rigorously very lower number, but the explanations need to be learned. It is a training that you have to go through. You have to read books for doing that. That's not part of strength of material. So tensor algebra, or tensor mathematics, tensor calculus that you need to learn will be part of continuum mechanics course if you take in your senior graduate classes. Okay, right? So, but learning that is very good if you stay in solid mechanics, if you stay in engineering mechanics division. That helps understanding of many things easy. So if you're interested, please give a search in Google. You will get millions of probably notes on tensor algebra. You don't have to go to very deep, but something you can. It's a shorthand kind of thing, so it will be useful for you while writing notes. Right? We learned that tensor is a stress is a tensor and is of order 2, and then also we learned few more things. Transformation of stresses. Okay, we learned with formula that is there, algebraic equations, no, trigonometric equations. So formula will write equations of transformation. And then we learned using Mohr circle. Right? And just now we learned another one, using matrix transformation. This is where we stand, right? And last class we gave two examples. We broke two chalk pieces, and we said all of you to do the analysis of those two chalk pieces, right? But I don't know how many of you have done it, so let's do it here today. Okay, what would you do? First one, I'm going to do for you is, we had this chalk piece like this. Let's say that it's a uniform uniform member. There is no tapering in anywhere. And what did you do? If you remember, we gave a force P on this side, an axial force P here on this side, right? And we saw that it broke like this. Okay, now take an element here. Let's take a small element there around this point here. Now if I look at that element, what are the stresses that are acting on this element? Can anybody write? The cross-sectional area is, let's say, A. What is the stress that is acting there? Just normal stress. Very good, Archie. So here is a normal stress here, sigma. And here is another normal stress, sigma, right? And there is nothing acting, only this. No shear stress, nothing. Let's say this face is called A plane, and this is called B plane. Okay, our definition. Now, can you draw Mohr circle for this? Jay, I don't know whether that's called fracture stress or not. Fracture stress is something different. We are not going to do fracture mechanics here. Yeah, it can be called a fracture point, but it's not a fracture stress. We'll talk about what kind of stress breaks it. We'll talk about ultimate stress. We'll talk about yield stress, right? So all these stresses we'll talk about. Bear with us for another few classes, maybe another 2 weeks, 1 week, not 2 weeks, and we will get into those, right? After that, we'll have a class, and I mean at least 2 classes on failure theories, right? So just don't take assumptions, don't make assumptions right now. Failure theory is a little bit more complicated than what you are talking right now. Yeah, okay, because you have already learned that any of the planes will not have only one kind of stress, it will have two stresses, right? It can have both normal and shear stress. Now, if they have both normal and stresses, how do you combine them to get the failure stress, right? Which category, under which criteria you are going to check them? So it becomes a little bit more complicated than a single directional stress, right? Single directional stress, I'll tell that it will go into plasticity. Once it crosses the yield, it will fail. It's a brittle material, so it will fail after its yield stress. So all those things we can talk about maybe in a 2 weeks time. But after that, there is a part of the course which is called failure criteria. So we will discuss on those things in the failure theory course. Okay. Right now, can you draw motorcycle for this? All of you. Is it possible for you to draw motorcycle? So let's draw the motorcycle. So this is the line. Let's say this is my axis. This is my sigma axis and this is my tau axis. Okay. Positive tau here, positive sigma here. And this is my sigma, right? I'll write it as P by A. And the plane has zero shear stress, right? So this plane, plane A, coordinates will be given by P by A, comma 0. So that will be where? That will be on this axis itself. So this is P by A, comma 0, right? So P by A, comma 0 is this point. What about plane B? That is 0, comma 0, right? So that's going to be this point. So this is my A point, that's my B point. And then I have to draw a circle between them, right? Aha, fantastic. So I've drawn a circle between them, okay? So that's my motorcycle. This is my motorcycle, right? That's my motorcycle. Now my center point, I know it will be somewhere here, P by 2A, right? Center is P by 2A, comma 0, right? Radius P by 2A, which will be equal to tau max at an angle 45 degree, right? So what is the zero line? If I ask you, what is the zero line? This is the zero baseline, right? Zero degree baseline. What are its principal values? Principal max sigma 1 and sigma 2. Sigma 1 is equal to P by A and sigma 2 is equal to 0, right? These are principal values. Sigma max, this is the maximum principal value and that is the minimum principal value, right? And what angles it makes? Theta P, 0 degree. So the maximum stress that is acting at 0 degree itself, right? Therefore, it's going to fail along that plane. Okay, clear? All right, let's look at the next one that we did. We had a chalk again.
Sir?
Yes.
So, the angle which you wrote, is it with respect to the Mohr circle or with respect to the surface, sir? Like
This angle?
Yes, 45. No, not that, sir. Tau max, 45 degrees.
Yeah, with respect to the main plane, not with respect to it. So, okay.
Okay.
Thank you. Who was this? Jaya or
Okay,
Archis?
Kanikesh.
Kanikeshwar. Yes, Kanikeshwar. So, thanks. So, this is your sigma tau max, right? Okay, P by 2a. So you can see that power max is P by 2a and tau is P by a, sigma is P by a. So 48 degree equal to 90 degree Mohr circle, right? Okay, clear? Yeah, I should have been clear. All right, so now this is what has been done. Now let's look at torque. The next one we did was we gave torque. So let's say this is a torque and this is a torque that was given, right? It was given ulta, right? Opposite. And this was its axis. Now you take a plane here, any small plane. What did you give? You know, if you want to draw it in an elemental diagram, it will be something like that. Okay, before I go here, let me also write the matrix format of this. Okay, the matrix expression for this is sigma, not sigma, it's only P by A. Since we know the value 0, 0, 0, right? The representation of that element. That's why it's a non-D element, not a 2D. Now here, what did we give? We give only shear, right? We did not give any normal stress to the material. So it was only shear. So let's say I have given positive shears. All right, I've given the shear here. I cannot tell you the value of shear stress here because we have not yet learned it to find how to find the value of shear stress. Okay, we will learn it probably maybe after a month. So we'll write it as shear. Okay, we will not write the value of shear stress. Now let's say that that's what has come here, shear. Now, how do I draw the Mohr circle for this? Again, I will first draw elements like this, axis like this. So this is sigma axis and this is my tau axis, right? Okay, so let's look at again the plane. This is my plane A and this is my plane B. So coordinates of plane A 0, tau, right? Positive because it's giving a anti-clockwise moment. All right, and plane B 0, minus tau because it's giving anti-clockwise movement, right? So that we have to be careful. So this is my, let's say this is my tau value. So that's my positive shear stress downward. So this is my point A. Okay, and similarly 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah. Okay, that's my point B 0, minus tau. And then what I have to do? I have to draw a circle between them. It's not very good, but yeah, okay. Right, so that's my Mohr circle. And what is my zero line here? My zero line is this guy, right? Because I've joined this one. So this is my 0 degree baseline. Why is this important? Because my angles will be calculated based on that 0 degree baseline, right? Okay. Now let's look at principal stresses. What are its principal stress? This is its principal stress, right? Sigma 1. And that's the minimum principal stress. That means sigma 2. So sigma 1. So now if this is tau, that is also going to be tau is equal to tau. Sigma 2 is also going to be equal to minus tau, right? Compressive. So that is on the other side. Okay. And it makes an angle theta p How much is theta p? Here it is 90. So it's going to be 45 degree. So you could remember that the failure happened at 45 degree. Okay. So the principal stress was maximum at 45 degree, nowhere else. And therefore it fell from that line. Okay. Now, can I draw the elements for this sigma 1? Can you draw the element for sigma 1? The element, if I have to draw, the element will look like something like this. Yeah, the elements will look something like this. So that will make an angle of 45 degree. That I can push back to sigma here. That will make an angle 45 degree with the horizontal. So okay, that's my sigma 1. And here also it is my sigma 1. What will be here on the top? What is the shear stress here? 0, right? No shear stress, because at this plane, pencil plane will not have any shear stress. What will be at the top? Top is 90 degree in the plane, and therefore in Mohr circle it will be 180 degree. What is the value at 180 degree? Sigma 2. So it's going to be something like this. Sigma 2, and it's compressive, right? Okay. That's the elemental diagram. Clear? I hope it's all clear to you. And it also clear why it fell around 45 degree angle. Okay. All right. So what it's a matrix. Matrix is going to be something like this. Matrix notation. This is 0. That is tau. This is 0. This is tau. Okay. That's its matrix notation. All right. Very nice. What are the other ways of finding principal stresses? Principal stresses. From the equations. How do you find it? Center O, radius tau. What is this sigma by 2? Did I make a mistake? Center is 0, 0. Radius is sigma by 2. Yes. Yeah, I have to write that, right? Yeah, sorry. Center is 0, 0. Radius is tau. Because I don't know sigma here, I know tau. Okay. So that is tau is the radius, not tau by 2. It's so tau is the radius. Anything else I wrote there? No. Okay. Anything else? All right. Now, how to find this? If you remember, we know the formula for it, right? The formula was given by, I don't remember the formulas, okay? So don't ask me. Yeah, these were the formulas. So this is your sigma x, right? So if you have this formula, can you just copy it? And can we just go here, not here, here, and paste it? Fantastic. Life is so simple. All right. So we have this, right? So now what you do is, you know this formula. You need to find maximum, right? So we need to find sigma max and sigma mean. That is what we have to find. And you know how to find that, right? So you have to take derivative with respect to plane theta, right? So max, so you also theta p, and then you have to put that sigma max goes to, sigma is maximum, so derivative has to go to 0. So you just take that, and then you can prove that the formula that we get is same as this. So this is given as assignment in the next tutorial. So do it, okay? We'll get it in books also, how to do it. So you have to take first derivative and put the derivative to 0, and we'll get that. Or you have to find shear stress and put the shear stress to 0, because shear stress will be 0 in the principal planes. There is another way of doing it. That is what that will not be available in the books. So that's what I'm going to tell here. Find eigenvalues of the stress matrix. Okay, you have to find eigenvalues of the stress matrix. And let's see, let's look at the examples that we have. First example was, matrix was sigma 1, 0, 0, 0, right? Remember, P by A, sorry, not sigma 1, P by A. Find eigenvalues. Can anyone tell me? The next one was 0, tau, tau, 0. Find eigenvalues and vectors. And you'll see you get back to the same result that we got here. Okay. So eigenvalue and eigenvectors of the stress matrix provides you the principal stresses and the directions of the principal stresses. It's not only for 3D, it's for 3D also. And that becomes very easier. For 2D, you have more circle to do it, your formulas to do it. But for 3D, it becomes difficult to use those formulas and also draw more circles, because yeah, thanks to that, because more circle is not going to be, here we are drawing more circle because we have two planes, right? So we are drawing it between the planes, that is this and this. But for a 3D, there will be three planes, right? Now in a 2D structure, you cannot do a 3D mode circle. So your mode circle will look like between different stresses, sigma 1, sigma 2, sigma 2, sigma 3, and sigma 3, sigma 1. So you have to draw three more circles in the same plane. Yes, so it's matching, right? Very good, Signal. So with that also you can find the, so for 3D material stress, it becomes very easy to find principal planes and the principal values of the stresses just by finding its eigenvalue and eigenvectors. So one of the application of eigenvalues and eigenvectors in matrix analysis, in continuum mechanics, is finding principal planes and principal directions. Okay. All right, very good. Here we have one problem. I think now you can do this problem. It won't be difficult. We have solved one similar problem. We have solved a similar problem like this just now before. So you can do this. Can you please try it? I will wait for a few minutes. And also you can do probably this one. So some of you try the first one, which we call biaxial state of stress, because there is no shear stress acting. Okay. And this is called pure shear because there is no normal shear acting. Okay, normal stress acting. So please remember those names. These names are important because they will be used left and right when you read books or papers, technical papers. All right, can you please solve and find at least the principal stresses?
So we should solve problem 2 or problem 3, sir?
Some of you solve problem, okay. Some
So
of you
like
solve
problem 2
problem
is
3A.
like this.
Yeah, some of you solve problem 3A and some of you solve problem 3B. Okay.
Sir,
Solve
in 3A,
A and B. Yes, in 3A.
Sir, both the normal stresses are compressive, right? Like, so the
Yes.
matrix will get -4, -1.6.
Yeah, that is also compressive. Yes, thank you. Yes, here it's correct, right? Yeah, 400, 400, right? So some of you do A, some of you do B. Okay. So I hope it won't be difficult for you to draw more circle quickly and do it. This problem also you can solve. The problem 2, I'm not telling you to solve now. You can solve it at your leisure. So there are two steel plates which are joined by a weld. The weld makes an angle beta. Okay. The loads are given 100 kilonewton on both sides. The thickness is given 80 mm, and the width is given 80 mm and the thickness is given as 10 mm. Right, are applied to the weld at angle beta has been given the angle. Determine the in-plane shear stress parallel to the weld. So you have to determine the stress parallel to the weld. Okay, and the normal stress perpendicular to the weld. So that means sigma x and sigma y both you have to find. And the principal plane stresses. So you have to then find the principal planes. That means you draw a more circle and you can do it. Okay, this problem please solve it. All right, so yeah, this is what we discussed just now. Negative shear is this. Yeah, so that I have already discussed. So sigma x does how does y does y does sigma y does will be given by cos theta sine theta minus sine theta cos theta sigma x sigma y. Sorry, tau xy. One minute. Yes.
So like here we are considering 2D bodies. So if you take 3D bodies, we'll be getting more spheres.
Yes.
Because
What is sphere meaning? No, more
First,
sphere. There is nothing called more sphere. Sorry. No,
like
we won't get.
if you
What
solve
happens?
equations, we should get a sphere now, sir.
If no, it doesn't come that way because it then becomes very complicated. It will depend on the Euler angles that we have. Okay. So it's not that it can rotate about a single plane. When it rotates about a single plane, it becomes very simple. Now it can rotate about 3 Euler angles.
Yes, sir.
Right. So what happens is so if you see the Mohr circle that we draw, the Mohr circle is between sigma x and sigma y, right?
Yes, sir.
Right. So what you do for a 3D plane, it's not part of your syllabus, but you will see in books. Mostly it will be available in civil engineering books.
Okay.
So if you have this, so we are this is my sigma and this is my tau, right? Now sigma and tau is not going to change. They will remain sigma and tau because there are only two stresses.
Correct,
So
sir.
you have to draw a circle between sigma x and sigma y. Then you have to draw another circle between sigma y and sigma z maybe.
Oh,
And then
okay.
you have to draw another circle between sigma z and sigma x.
So like for the cube also, we will take each face of the cube and analyze it, sir.
Right, right. That we will do. And then there is a way of finding principal stresses. Okay. So
Yes.
it's a little bit more involved and more complicated than normal 2D analysis, planar analysis. And that's why it becomes easy if you do eigenvalue analysis and get it. Eigenvalue analysis will be much easier and it can code it in MATLAB also. MATLAB
Okay.
also. That's an advantage of doing it.
Yes.
Okay.
Yes, sir.
Right. So I have also talked about how to determine principal stresses for matrices. So with that, I'll stop here.